So I'm Gabriele Russo from the Vergata University of Rome. This is not a proper demo. I'll actually be telling you about some ongoing work we have been doing on architecture-aware load distribution in heterogeneous edge FaaS systems. So our work is motivated by two related trends. One of them is that the function as a service paradigm is increasingly adopted at the edge of the network beyond traditional cloud data centers. And at the edge of the network, you have to face the additional challenge of having constrained resource capacity. So you cannot accommodate the entire workload at the edge. The other challenge is that the infrastructures where serverless functions are executed are increasingly heterogeneous in terms of capacity, CPU architectures, availability of accelerators like GPUs. So the challenge of heterogeneity in the context of serverless computing has been studied in the last years. Several works focused on the problem of load distribution, so how to use heterogeneous hosts to serve incoming requests, accounting for response time, carbon footprint, and so on. The work closest to ours focused on, in particular, on the CPU architecture, trying to understand if functions have some architectural affinity. So if a function is, I don't know, faster on ARM compared to x86. So in particular, the existing works try to leverage limited profiling data to predict whether a function will be faster on a certain CPU architecture rather than the other. The approach we are working on actually tries to solve both the problems at once. So trying to discover if there is some architectural affinity for a function, and also decide how to distribute the workload among different architectures based also on the current availability of nodes and so on. So we are working on a two-layered approach. When we receive a request, the first layer is a multi-armed bandit agent, which has to decide which architecture to use for a certain function. So basically, we are trying to learn online which is the best architecture for a function in a certain moment. And the second layer is a traditional, let's say, consistent hashing approach that is used to forward the request to a specific host once we have chosen the architecture. This is similar to what OpenWhisk does, so it's pretty standard. So the novel part is the multi-armed bandit approach, in which we have one agent for each function. And the goal of the agent is to learn which is the best action, x86 or ARM, for instance, online, so based on the observed performance of the function. It tries to maximize a reward signal, which is formulated in terms of function response time, but it will be easy to include other metrics like cost, energy consumption, and also contextual information. So for instance, you don't want to always pick the best architecture, because if one architecture is running close to full capacity, the agent might prefer to choose the suboptimal architecture for a while. So we have some preliminary results. We implemented this approach in Serverless, which is a research prototype we developed in our group. And we compared it to an architecture-unaware approach, which is the default OpenWhisk scheduling policy, using 9 different functions which have different architecture affinities. So some functions are significantly faster on x86, some functions are equally fast on both the architectures. Our results show that for almost every function, our approach is able to reduce this response time. And on average, we have a 17% response time reduction using our approach compared to the default OpenWhisk approach, which is not aware of the architecture. So this was very quick. The results are promising, but of course, we need to further validate the approach using a larger scale setting, including multiple objectives along with response time, and possibly extend beyond the single two architecture, x86 and ARM, possibly including some accelerators like GPUs, because this is fundamental for serverless AI, as we heard before. So if you have questions, I'll be around on Discord and also during the week at Devs. Thank you for your attention.
Thank you very much, Gabriele. you actually made it very fast, like not 5 minutes. So if there is a question, you can ask right now in Zoom or Discord, or ask Gabriele directly in Discord. If not, Daniel, you can start your presentation.
We have one question here.
Okay, one question. Go ahead.
Slide 7. And if you can maybe repeat the question. Yes, so the average, I think it's weird because you have this imbalance. So can you explain why that benchmark produces that result?
Okay, so maybe the question is why we have this imbalance. So part of the answer is that we benchmarked the functions on both the architecture at the beginning, and you can see that some functions have some affinity with one architecture or the other. So for instance, the limpak function, which is a micro benchmark, is definitely faster on x86, while most the other functions have not much difference if you run it on ARM or x86.
Which ARM processor is this?
I have to check it. I'll tell you later. So the results we have with our policy partially reflect that behavior, because if there is no affinity, you cannot have much gain. But also we have this strange case for one function, which is a encryption micro benchmark, in which actually our approach has no benefit, and we have to investigate this. But I mean, most of the reason lies in the nature of the workload, which can be faster or not on different architectures.
Okay. So, looking at your approach, you are doing, as you said, it divided into 2 parts, right? The first part is figuring out which architecture works best, and the second part is like basically placing them, right? Mm-hmm. So most of the benefit which you're showing, the 70% the speed up, is it coming out of figuring out which is the biggest contributor to your benefit? Like, is it the first part figuring out the right architecture, or is it the placement part which is contributing?
Basically, the second part is the same using the baseline. So the benefit lies in the first part.
So learning which architecture performs the best, right?
I think we have another question.
I do not have anything that I see online, so I think that's it.
One more?
Yeah, go ahead. Sorry, I cannot see the room, so you go ahead.
So you said you're using context information to decide or to learn which architecture is best. Can you speak a little more details what kind of information?
Yeah. So far, the only contextual information we used is the utilization of the 2 pools of worker nodes we have, so x86 and ARM. The reason is if for some reason at some point you have very few ARM nodes, they may be overutilized. So you have to balance this overutilization with the benefit you have in running a function on ARM rather than x86. So the agent tries to also balance the load on the 2 pool of worker nodes using this contextual information. But
other information?
For instance, you might include information about the, I don't know, carbon footprint of the different nodes at some point, or user preferences, something like that. So I think the framework could be extended in various ways in that sense. Thank you.
Okay, I think we are out of time. Daniel, please start your presentation.
Hello.
We can hear you. Good.
Okay.
Go to presentation mode. Yeah, perfect.
You see it?
Looks very good.
Okay, perfect. So, hello everyone. My name is Alejandro Tejeda, and today I'm going to introduce you to PyRun, a platform designed to completely redefine how we approach serverless Python and artificial intelligence in the cloud, and more especially on an educational environment. Our mission is built on 3 pillars: multi-cloud flexibility, simplicity, and being fundamentally AI-powered. And to understand why we build PyRun, we have to talk about the cloud complexity tax. Right now, developers and data scientists spend up to 16% of their time just fighting with infrastructure instead of writing code. You have a Python script that you want to scale, but suddenly you are forced to navigate between security roles, network, Dockers, and permissions. And this is translated into high cost and a lot of time managing and configuring all the infrastructure and very time to market, very slow time to market. So that is the exact problem that PyRun solves. We have built a unified platform that abstracts away this complexity, allowing you to go from zero to cloud in just 2 clicks. And as I said, this platform is not only allow you to deploy cloud resources quickly and efficiently, but it's also designed for an educational environment where teachers can have greater controls and more easily teach basic cloud concepts to their students. To this end, we recently created a course system where teachers can monitor who their students use the platform, including their own users, and who they are using the artificial intelligence, all integrated into a single educational focused platform. And to see how it works, I have the PyRun.cloud webpage, where here on the home page you have a simple dashboard where you can see some information like the total executions, the AI budget for your user, and some kind of information. And also for us, it's very important the simplicity and the that you can run any pipeline or any example to start working with PyRun with just 2 clicks. So for that, we created the pipeline section. Is some examples of real world examples of, for example, precipitation frequency changes or image classification with AI, water consumption. Here you have a lot of examples that you can start working with them with just 2 clicks and the run button. And also we have recently some AI tools like MCP, Hugging Face Model Explorer, AI Coding Assistant, for example. And as I said, the new feature of PyRun is the course section where you can manage all of the information from your students. For example, in this case, we have the course of distributed systems. And also you can see the information of each student. You can see the workspaces that this student has, the pages that visit this student, the AI budget, for example. And also here you have some aggregated information from all of the courses that you have. And this is a super powerful platform for an educational environment. And returning back to the presentation, major focus for us at PyRun is to democratizing this technology. Cloud computing shouldn't be locked behind step learning curves. This is why, apart from everything seen so far, we also build the Learn Labs. These are interactive AI-guided environments where users, from students of the university to senior researchers, can learn complex cloud architecture by doing. That it's so important. With native support for open code, for example, GitHub Copilot, custom AI skills, wherever you want. And wherever you are migrating a simple Flask app to API Gateway and DynamoDB, or doing distributed climate analysis with satellite data, for example, the AI acts as your personal principal cloud architect, guiding you every step of the way. And this is just the beginning. We are building the future of cloud. Sorry?
You are out of time, but finish.
Yeah, it's the last slide. This is just the beginning. We are building the future of cloud data science with features like data cockpit for smart partitioning and ready to use AI pipelines. And thank you for your time.
Do we have questions in the room or online? to Daniel.
Before we start, I want to say a quick note that the following demos you're going to see are pre-recorded. They are real executions, but we have embedded them as videos so they fit within those 5 minutes. Welcome to my presentation. I'm Octavio Iacoponelli, and today I will talk about BlocksDB. Context. Vector databases are now a core part of retrieval augmented generation and machine learning systems. But in practice, most of them are hard to operate. Cluster-based systems like Milbus, for example, struggle with bursty and Spark workloads, and there are other serverless vector databases that are still on their early stages. What we found is that the real bottleneck is not similarity search itself, it's the data partitioning and how systems scale under dynamic workloads. BlocksDB is a serverless, stateless vector database. It's a command line interface first and built over AWS Lambda, S3, and DynamoDB. The core idea is simple. Instead of maintaining a single monolithic index, we split the data into independent blocks and distribute computation across serverless functions. This removes the need for clusters or dedicated infrastructure. Let's start now with the setup. With a single command, we can deploy the entire system. We just need to provide the AWS credentials and a bucket. Everything else, the Lambda, the storage, the pipeline, is automatically provisioned. After waiting a little bit, the database is ready to use. Now, we can create a database itself. We run the initialize database command with a source dataset in CS, comma-separated values, and a number of workers. This dataset is distributed then across Lambda functions, and each worker builds parts of the index in parallel. This produces an independent index, blocks that are back then stored in S3. At this point, the database is fully operational. Now, let's see how to use it. We can insert new vectors using the put command, for example. We can then test the status of the database after doing a put. These vectors are immediately available on the system even before the indexing. When you insert them, they first go through a phase where they wait until to be auto-indexed. But they are always available. We can also attach tags, which allow filtering during query time. And then when we query, we can set both the indexed and non-indexed data, and optionally filter by the tags. This means that the system stays fully usable even while data is still being ingested. So you can do pre-filtering on pending files or post-filtering on already indexed dataset, etc. Beyond this core workflow, there are some key features that are worth mentioning. Like, for example, you can run multiple vector databases inside a single bucket. You don't need to provide multiple buckets in order for it to work. Everything is fully configurable through the command line interface or via config files that are already provided as a template so that you can modify. You can also extend or modify the block implementation itself, so you can see the parameters of the indexing type and the number of workers, etc. Also, you can retrieve back the vectors by doing a get by ID or by tags, depending on your use case. As for benchmarks, we have evaluated BlocksDB on the deep 1 million dataset. We compare it to LanceDB PQ variants, where we achieve a higher recall with a significantly lower latencies. As you can see on the graph, on a single index, a small index, but on a single index, we are getting way faster querying and way higher recall. Also, when comparing to other systems, such as S3 vectors or Milbus, we can see that overall, we are competing in the indexing times, only losing to Milvos in the Deep1M dataset, and in the GIS1M, winning above all the other comparisons. Finally, we have some future work. As of right now, we are actively developing this application, and we want to introduce things like on-premise execution, so that you can run BlocksDB on your cluster. So there's no need to be tied with AWS. Finally, I want to close it by saying that BlocksDB shows that a vector database can be fully serverless and stateless without sacrificing performance or features. Right now, we reduce the whole system to pretty much 3 or 4 commands. But, query, initialize database, and get. Thank you for your time. This will be all. And if you have any inquiries, you can find me on Discord. And also, you can see the project link right here.